So I'm Matthias Pavet. I work at the WSL Institute for Snow and Avalanche Research in Davos. And you see, this is work that has been done over several years or many years with several people, both from Davos and from other places. And actually, my topic is really how to produce fair data with less pain and more reward. And I want maybe to clarify what is my focus. And my focus is on 1D time series. So basically time series of 1D parameters, such as what is coming out of automatic weather stations or permafrost thermocouple chains or hydrological discharge. I want to clarify also a second point of focus. I'm focusing more on research data because you have like large monitoring networks that are made of lots of identical stations. So I'm thinking about WMO network, for example. And here it's less of a problem. What I will talk about could still be applied, but it's less relevant because the stations are the same. If you look at research automatic weather stations, these are stations that have been installed to answer a specific scientific question. And you see some example here below. And you can see the stations are widely different in terms of the setup, the height, the instruments that are installed on it, the location and the surroundings and so. So it brings me to the first challenge. This is the diversity. This is a very large diversity in terms of measured parameters, in terms of sampling rates, also sources of data. So the data being pulled out of a data logger is going to be stored into a database, into a web service or flat files or so. It's a challenge in terms of data formats. You have all kind of data formats. Most of the time it's variants of CSV files, but CSV files are not really tightly defined, so it can be very much anything. And you might have also changes into the station setup and both hardware and software, and so the station's output at any time, any number of times during the station's lifetime. So I give, for example, here the Davos Chilberg station. It's slightly above Davos at Wahhavi station. It's an automatic weather station that has been running since 1975, and it has seen lots and lots of changes, both in the type of sensors and number of sensors, as well as the sampling rates, and also the location. It has been fully rebuilt several times, and nobody really looked into the old data. So lots of things went unnoticed, and lots of metadata was missing. I show you here, this is a small extract from a real data file. I just truncated the number of fields because there are just way too many fields to show. You see it was more than 100 fields. You see that actually just based on the sensor name that they give here in the header, you need to distinguish that you have multiple stations that are written within this one file. Of course, without the metadata, it's really challenging. You can see here the first column, this is like the year, but just on 2 digits. Then you have a month, the day, some kind of numerical time, and you have to be able to parse it. You have also changes in the number of sensors within one given file, or also sensors, so columns that are swapped over time. And of course, it doesn't match the header. Here, this is the same station, but fast forward to year 2000. We still have multiple stations within one file, but now we have a station number, at least to distinguish with an index which station it belongs to. And you see the number of fields is widely different. The naming scheme is totally different too. So this is really a challenge. Now, when I was a young researcher, I had this kind of ideal view of scientific data publishing, where a researcher is going to spend time to carefully prepare his or her data, standardize everything to a common format, common metadata standard, common naming, filtering spurious data, filling the gaps, and so forth. And then he or she is going to publish the resulting data. And you have high quality data that other people can reuse, and it's suitable for a paper. And then time went by, I grew older, and I got a more accurate view of scientific data publishing, where this is more this kind of workflow. You have a succession of trial and errors. Each new cycle starts with the data that was produced in the previous cycle. You have manual tweaking of the code. Most of the time, it's that you have a piece of script that somebody gave you, and you comment out one part of it, and you uncomment another part, and you change which you have commented out, which you have uncommented. Of course, in this case, you don't keep track of what you have manually tweaked. You have combination of multiple software snippets and tools. So it can be different tools, even running on different platforms. and you have pieces of software, pieces of code coming from one place and another place, and you just combine everything and hope for the best, more or less. And you might have even manual tweaking of the data, that you go into the data file to change some stuff so it works properly for you. So of course, in this case, you have some issues. First, it's usually not standardized. So it's going to be difficult and tedious to reuse the data because you have all kinds of formats, all kinds of parameter naming, all kinds of units. And you can see here, it was a survey we did in 2020 for Global Cryosphere Watch. And the question was, how do you read data coming from third-party sources? So not the data that you deal with on your daily life, but when you get data from somebody else. And as you can see from this survey, it's basically the vast majority, you have to write an adopt script to read it, or you make some changes into your own source code to be able to read it. And it costs you some time. It costs you a day or a few days to read it. So it's very inefficient. Now back on our workflow, this kind of chaotic workflow is not reproducible. Even if we pretend it is, even if we believe it is, because you have all of these trial and errors, all of these steps, actually, it's in the end, it's not possible to reproduce. And it's also error prone because you're trying and trying again, and you might just make errors and not really realize what you did. Overall, it's also very time consuming. It's often done very late after the measurement. Most of the time, it's you write a paper and, oh, I need to publish the data. So you just rush to try to get the data published. And it was maybe 10 years after the measurement. So that means that most of the metadata is missing. When there are some changes into the station setup 10 years or 20 years ago, it's already forgotten and you have to go dig into log files, logbooks, and so to try to understand what happened. And so it takes even more time. And overall, it's not really fair data. In the best case, it's findable and accessible only. So what we need actually for fair data as a basis, we need standardization. So that no matter where the data is coming from, when it is published, it's everything in the same format, with the same parameter naming, with the same metadata standard. And so we can use data from different sources in a transparent way. The second point, we need reproducibility. That's a way to validate actually that we understand, we know exactly what we have done, so we can regenerate the exact same data at will. And it allows us to regenerate the same data maybe in an hour or maybe in 50 years. So we all talk about fair data, but actually in real life, the standards are complex. When you need to standardize your data, it's complex. You might have several hundred of pages of documentation to define the standard. You might ask yourself, but which standard should I use? You have multiple ways of standardizing your data along different standards, and you're not so sure which one you should follow for your use case. The implementation is time-consuming. It's difficult, maybe quite complex. You might have lots of details to take care of, so it's really time-consuming. And even when everything has been implemented, even if you have a tool to do it for you, you still need to inject the metadata or to enrich your data with metadata. You still need to do some cleaning and ideally to check that your data in the end is still compliant with the standard. So it's very time consuming. And I can ask myself now as a researcher on top of my duties, should I invest so much effort and time so that random people on the internet can use my data? And here it's really fair, just frustrating, annoying, intimidating, and rewardless. So now we'll do some role swapping. I'll try to look at things as data creator. And as the saying is, you know that you need to eat your own dog food. So as a data creator, what do I want to make my life easier? I want to be able to produce data sets on demand. So if I have a student walking into my office, who requests some data, I could just say, yes, sure, no problem. I just regenerate the data, I gave it to you. So it means that word processing needs to be automated. Ideally, everything is integrated in one place, in one tool. So I don't have this kind of patchwork of different tools. And what I want also is being able to handle all of the station's history in one go. So generating the data from 30 years ago or the data from last week is going to be the same in the same tool and the same way. I don't see any difference anymore. I want to be able to collect the metadata that is relevant to dataset production or dataset use as it happens, so that this is still fresh in memory. I would like to have also push notifications when something goes wrong. So I don't have to look at my data like every day or once a week or something, but the data will come back to me to say there's something that doesn't work as expected. And I would like to be able to publish a new data set with a few clicks, just as a snapshot of a current data flow. And overall, I want to have as little to do as possible because I'm busy with so many other things. So this is what I call scientific data publishing made easy. What we do in our design, we have all interactions with the data through a single configuration file. And the whole history of a station is contained into this ini file. We have a data processor that is going to produce standardized and quality control data from the raw data according to what has been described into this ini file. And when new data comes in, it's processed 24/7 automatically. So I can use it for operational applications, and I can use it just for my regular usage of data, like, again, as I said, for modeling or for a student or something. Because I can use it, I have higher chances of spotting issues on a timely way. And it creates this kind of progressive refinement of the data over time, because I spot some issues, some corrections that could be improved or something. I put them into the ini file, and it will regenerate the data along these lines. And then if I track also all the changes, I can reproduce always what was the status of my data set at a given point in time in the past. So I mentioned this data processor. What is this data processor? And here, this is Meteor, the data processor. It's a meteorological data preprocessing library that we started developing in late 2008. It has been used since then for operational avalanche warning applications, and also now for datasets production. And it is open source. The principle of operation for Meteor is that it goes through this fixed series of processing steps and between the raw data and your standardized data. So first, by reading the data, you choose the format through a system of plugin, and you can so adjust to a large number of input formats. Then you can apply low-level addition or filtering or corrections. You have lots of algorithms you can choose from that you can combine at will, and you can even time restrict some of these. So if you had a period of time 20 years ago when you had to apply an offset correction on your snow height, you just declare it, and it's going to be only applied for this 1 week 20 years ago. You can then choose from different output formats, again, through a system of plugin, and also enrich with metadata. And nothing is hard-coded. Everything is coming from this configuration file. And the goal is that this configuration file should be high-level and understandable by a human, let's say in 50 years from now. So I show you here an example of configuration file. It's a real one. It's one that runs, that creates some data for Weissflur site for us. You see that this is structured in sections. And for example, here we define the plugin is going to be a CSV for reading CSV files. And we define also the location. It's into the input directory that will find the files. Here we define some basic geographic metadata. So the coordinate system, the time zone, we give a name, we give an ID, and the geographic coordinates. In this next section or next group here, we define how to read the file. What is the file structure, like the delimiter, number of headers, which fields are present in which order, how to read and parse the time. Then we list all the files that are read by this data set. And actually here, this is kind of an old example because now I've renamed some of the keys for clarity. For each file, also, we can redefine the parsing. So we can have some files that are parsed slightly differently from the other ones. And we can also support line restrictions, as we can say you parse differently the first 1,000 lines and the rest of the file. Here we apply some corrections. So here this is for unventilated temperature with the UVALT correction. You can look on Google Scholar, you will find the paper. And finally here into the output section, we define the format. So it's going to be a netcdf. The directory will put it into the output directory, and then we also define some metadata. I put just very little metadata here, so we don't have a very, very long screen. Everything fits into one screen. So now if we go back into our workflow, thanks to Meteor.io, the data is going to be standardized. it's going to be also reproducible. We have no manual tweaks. Everything is defined into the ini file. We also write a Meteo.io version as a Git hash into the metadata, so into the data files. So if you back up the raw data, you back up the ini files, and you back up the Meteo.io version, and then you can reproduce your output data. So it's nice to have a great engine, but you need more. Somehow you want something you can use this engine. And here, that's why we developed a whole ecosystem, a whole system all around Meteo.io. We have a graphical user interface for writing the ini files. This is initial, as you can see here on the screenshot. We have something for data visualization as embedded. It's based on Nibis. We have a web graphical user interface to run Meteo.io and to provide several useful services like data access, remote data access, data sharing, cron jobs, and so on. And you see, for example, here, this is a view of my data sets on the system, where I can see which data sets I have, if they are public or private, how many cron jobs, how many versions, when was the last cron job, and so forth. And we provide also web services for interoperability. So embedded into it, you have OGC, WPS, we have OpenDAP, we have Threads, we have MQTT. And so it makes a new workflow for working with scientific data from automatic weather station or similar. As you can see here on the left part of the screen, this is your automatic weather station on your system, where you read the data loggers and you put the data somewhere, and you make it available either as just a shared drive or a database or web service. On the right-hand side, this is more data portals or publishing platforms. And here in between, we have Meteo.io that provides what I call the Meteo.io data refinery. It provides a remote data access, it provides the data sharing, and it runs Meteo.io in between. And then you have this refining cycle where you can look at the data, or you get notification from the data, you look into it, you change your ini file, you commit your changes, and it runs 24/7, and you can always react and change and improve or refine your data. So it makes scientific data publishing attractive because we reduce the cost. Here, we reduce the cost by reusing metadata between data sets for a given data owner. Everything that is about your affiliation, your name, your field of work, and so you can reuse it between data sets, so you can define it only once. We offer multiple ways to connect to the raw data, so you don't have to push the data or have another cron job to push the data. You can just go directly connect and pull the data that you need. We give you notifications, so when something doesn't work, the data will call you and tell you it needs you. We also increase the benefits, because now, thanks to the system, you have something that is reproducible with versioning. We give you automatic data QA with notifications. You can produce multiple versions of the same data set, so different time range or different formats or different quality levels. You have this one-click or almost one-click publishing to data repository because you have all the metadata that you need. So you just push the metadata to the repository, and then the repository can just offer you to validate. And we offer you multiple ways to share the data, as well as an embedded data portal, a lightweight data portal. And on top of that, your data is verified. So now it's finally accessible, intuitive, and rewarding. I want to show you some screenshots. If you are logged in as data owner, here, for example, you see, as data owner, my data sets are permanently on the system. What it means is that my configuration is permanently on the system. The raw data doesn't need to be on the system, but at least my configuration is on the system. I provide the source data or the connection to the source data, and I provide my ini file, and anonymous users will be able to see my public data sets. You see here, this is this environment variable as data owner. I can see in my profile, I can define all the environment variables that I want. So here I define the ones for metadata, because all of these metadata fields are going to be reused for me between all of my data sets. And I can always overwrite them per data set or per cron job. Here I show you this is the definition of cron jobs. And here you see on the bottom of the screen, there's this variable name and value. So this is where for this cron job, I redefine some of the variables. I overwrite the definition of the variables. And here, this is a vision of a versioning for a specific data set. You see all the different versions with the commit messages and when it was done. When you logged in as guest user, you can see this is our lightweight data portal here. You see the map and the data sets, but you can also examine the metadata, you can ask for a rerun, or you can download the data as it has been generated. When you click on the data, you see here the different runs. And if you request a rerun, you can see here, you can choose if there are multiple ini files for it. And you can define, for example, the time range or the resolution. I want to show you a few screenshots here overall on the system. For user logins or user management, we support several systems with LDAP, with OAuth, with ORCID ID or email. Here you see this is on my dataset with my ini file. I'm currently making some changes, so I have this warning that this is a pending revision. I can try it, but then I should either cancel it or commit my changes. Here, this is the view of my dataset. Again, as I showed already, here, this is the view of the versioning. You see for a specific version, I have my commit message. I can do diffs. I can also change the commit message if it needs to be clearer, or also delete this configuration. If I delete it, it's not going to be visible, but I will keep track that there is a version. The goal is just in case if you, by mistake, committed some credentials, I can still delete, so nobody will be able to see it, but we still know there is a version and we still know what was in there. And here, this is the inheritance for the environment variables, so mostly used for metadata, where some are provided by the system, by the sysadmin, but again, you can overwrite them if you want. Some are defined into my user profile, and you can see on the lower part, the dataset, this is some that are defined with the dataset level. I could still have another layer, which is on the cron job level. And here, this is for the data QA. I had the data QA run, and we see there's just on the lower left, you see there's one little dot that is for the filtering. So here, on a relative humidity with a Tigan sensor, there was one point before January 14th that got filtered. I could click on it and see more details, but I know at least here something was filtered because it was not deemed to be a proper value. And I see on the right-hand side of the screen, I have missing values. So here they are all together for all the sensors. It just means that basically the data is late incoming. And then as a data owner or data producer, I'm happy I have a system that supports me, that helps me to create good data. You can see more or read more about all of this system with a paper on Meteo.io, a paper on Initial, and an earlier version of a system that was without the graphical user interface that is web-based, but it was for global crowdsphere watch. And thank you.